All right, here we go. Let's see what we can do. So, and this is really the physics section of the course. Now, where we're going, we're starting off with forces. From forces, we went to work. From work, we went to potential energy, gravitational potential energy. And then we went to kinetic energy. And the last part is the last thing, and that's the conservation of energy. You have a question? You just watching?
No, it's 10 a.m. and there's like a scheduled mini group break from 10 to 10:30. It's optional, and it is freedom of lecture.
You guys want a break? Or should we just do this? Keep going? Okay. I have a feeling the sound quality is going to be lousy on this video, but that's okay. So let's deal with forces. So, Hannah, what's a force? Excellent. You are like my best student. I thought that was a pretty nice set, so you could just smash it over. So we're dealing with forces as a push or a pull. And there are lots of different types of forces out there in some ways. In some ways, there's like just a few. We have like the strong nuclear force. The strong nuclear force is what keeps the nucleus of an atom together. You have the weak nuclear force, which causes radiation to happen, or radioactive decay to happen. And then we have gravity. And gravity is actually a pretty weak force in terms of these other forces, but to us, it's one of the biggest forces that we deal with all of the time. So gravity is always there. Is there gravity in space?
Yes, no.
Riley has this quizzical look on her face.
Say no.
It's pretty common to say no, because they talk about zero gravity in space. And why did they talk about zero gravity in space? Because you're floating. So, here's the Earth. Anyways, where are they floating? In space. But what are they in when they're floating around in space? In the spaceship. So in the space shuttle or in the International Space Station, whatever. What's our description of where that object is, besides just in space? Out of the atmosphere? How about in orbit? Does that work? Why does something go into orbit? What do we mean by orbit? Okay. Like generally when we talk about something being in orbit, we talk about it going around the Earth, and it keeps on spinning around the Earth. Why does it go in a circle? Because there's a wind but not wind. Interesting, because there's a force. Because there's a force of gravity towards the Earth. And it's the force of gravity that keeps it going in a circle. Why do we have winter and summer? Because of the sun. Why does we orbit around the sun? Why do we move around the sun? Because there's gravity. So it's the force of gravity between the sun and the Earth that makes the Earth travel around the sun. It's the force of gravity between the Earth and the moon that makes the moon go around the Earth. And it's the force of gravity on the space station that makes it go around the space station. So then the question is, why do people float in space? Maybe you never thought about it. Let's say we built a tower. This is not really important for you to understand, but I think it's a good conceptual idea of what's happening with gravity and understanding weightlessness in space. So we're spending a little bit of time on this. We had a big cannon on top of a tower, and we shot the cannonball out of there. What's going to happen? It's securely mounted on there. So the cannonball is going to come out. Eventually, what's it going to do? Well, it'll hit something. It's going to fall. It's going to go down. It's going to hit someplace over there. Does that sound good? Okay. So the question sort of comes in, what happens if we make a bigger gun? Excellent answer. It's going to go further before it hits the ground. So let's be really silly. Now let's say we put a big cannon, and this is the Earth. And so we could shoot it and shoot it further, or if we make it even go further, it goes further and further around the Earth. And so the whole idea of having something in orbit is that we shoot it so fast that it keeps on falling, and as it's falling, the Earth keeps on moving away from it, as it were. The curvature of the Earth. And so it keeps going all the way back. Now, I first learned of this from Bugs Bunny. You ever remember he takes the baseball and chucks it off in one direction, and he turns around and catches it coming from the other direction and has all the stickers of Paris and New York. You gotta love Bugs Bunny. But that's the idea. And so when things are falling and when they're in free fall, they're weightless because everything else is falling at the same rate. To simulate weightlessness for astronauts, they will put them into airplanes. And they'll take the airplanes up and they'll go over. Yeah. And so they can simulate or what's happening is that the plane is falling at the same rate that gravity's pulling everything down. And everything falls is accelerated at the same rate by gravity. That's kind of the weird thing. We think of heavy things falling faster. They don't. Anyways, all right. So coming back to gravity then. Continuing on with gravity. We can calculate gravity near the surface of the Earth through this simple formula, where Fg is the force of gravity. What's the unit of force? What's the symbol? N, capital or lowercase? Remember what it's called? Newtons. I was trying to set it back up for you. M is the mass. That's in kilograms. And G is a constant. It's not gravity. Gravitational field strength. And it has a value on Earth of 9.8 newtons per kilogram or meters per second squared. Now, sometimes what we do to make algebra a little bit easier when we have an equation that has three parts to this, we can do like a triangle or a circle or a square or whatever. And we can put the letters of the formula into that. And what this allows us to do is to quickly understand how we solve for certain values. And the way we do it is that if we were looking to calculate the force of gravity or whatever we're trying to, we just cover that section up and take a look at the other variables that are there. So if we want to calculate the force of gravity, we're going to take the mass and multiply it by the gravitational field strength, which is what we have up here. If we wanted to calculate the mass, if we knew what the force of gravity was, well, we cover up the m, as we see, to calculate the mass, we're going to take the force of gravity and then divide that by our gravitational field strength. If we wanted to calculate the gravitational field strength, we can take the force of gravity and divide that by the mass. Does that make sense, Riley? Am I going too fast, or I'm not wanting to go? I want you to keep up, be able to keep up. I can always print this out as well for you too. All right, so let's take a look at a question or two. I was going to do this. It's not quite.
What happens when there's
Is there a question? I don't remember what that question is exactly. Yeah. Not knowing what the question actually, how the question is worded, I'm not sure. Like, I would actually have to take a look at that. Could it be a mistake that I made? Possibly. I've been finding I make mistakes on some of these things. Not that I try to, but it does happen. Sometimes it might have been in the form of a question that on Earth, this is what the mass is, and this is, or this is what. Do you have the actual question?
Well, there's one on the
No, there's not. Let me do. I'm just going to do a simple one, then I'm going to do that one. Okay. So your question number one is, what is the force of gravity on a 32.5 kilogram rock? So 32.5 kilograms, we recognize that as being a mass, and we want to know what the force of gravity is. So we cover up the force of gravity, and we see the force of gravity is equal to mg. We're not given the value of g. And so because it's a constant here on Earth, you're sort of expected to know it. But, so we go substitute in our 32.5, g being 9.8 newtons per kilogram. Because you're allowed to have a cheat sheet, that information would be there. And a lot of times it's included in the question as well. And so we go multiply these together, and you find the force of gravity then is 318.5. Pretty simple, straightforward. It's just a matter of making sure that you put the numbers into the right spots. This is the format that I like you to do questions in. It gets you to think about the information that comes from the question. It shows me that you know the form of the equation that it needs to be in, substituting your value, and then doing your calculation. So questions like this, I would generally mark out of 3. I'm not necessarily giving a mark for that, but I'm looking for this, this, and this as being your 3 marks. And it's more, if this came out to be 3.18, you punch something wrong in your calculator, it's the wrong value, you'd be getting 2 out of 3. And so it's just, by making a question worth more than just 1 mark, I can give you partial marks for the work that you can't do or have done. Calculators lie. Like, I punch in the right numbers, I push equals, and it tells me a wrong number. It just happened. But let's go to this question. It says, a 17 kilogram dog on the moon weighs 28 meters. So then the question is, what is the gravitational field strength? So we're going through, we got 17 kilograms, that's M. We have 28 newtons, that's the force of gravity. And then we use G is equal to 9.8 newtons per kilogram, because we're expected to know that. And so there we've got our three values, right? And this is does this accurately describe where you went wrong, or what, the problem that you had? Yeah. Where did this number come from? It's a given number, it's a given constant. Where is this dog? On the moon. This value, this number of 9.8, is only valid on the Earth. And so if you go to the moon or go to like an asteroid and so whatever, there's going to be a different gravitational field strength because there's a different amount of mass within the planet or the moon or the asteroid that exerts a different amount of gravitational force. Does that make sense? Right. So here, the question is, what's the gravitational field strength? Well, what symbol do we use for gravitational field strength? Little g. And so what I'm reminding you is that because this is on the moon, yes, g is 9.8 whenever we're doing questions dealing with the Earth, but because this is a moon, that's not the value. And in fact, that's the value that we're being asked to find. Does that make sense? So we would take our triangle, which was F, M, G. We cover up our G, so we can see G is equal to our force of gravity divided by our mass. So then we'll take our 28 newtons, divide that by our 17 kilograms. And when it cancels off, that's 260 solar. And that's equal to 1.6 newtons per kilogram. Okay. Does that make sense? So while you're thinking that the question has all three pieces of information in there, they might actually be asking for you for something that normally we would have, but it's different in this case. Does that make sense? We can be pretty tricky when it comes to asking questions. Does that make a bit of sense, Robin? The calculations, the math, is not really difficult. It's the physics and understanding the concepts and so on. The words, yes. Curse these word problems. Sir, can't you just tell us what the buttons to push on a calculator? So let's deal with work. Simply, work can be calculated by taking a look at the force and taking the force and multiplying it by the distance moved. So, remember this picture? So, I've got a bag of groceries on my truck. And I'm going to take that bag of groceries, I'm just going to slide it off the back of the truck. I'm going to hold it, bring it in, go up these stairs, bring over here, and slide it onto the counter. Okay. The weight of the bag of groceries is 100 newtons. What I want to know is, how much work have I done? And really what I'm doing is I'm jumping into a difficult one So here, different question. Did I do work when I walked 3 meters? Was there a distance? Yes, there is a distance because we have that 3 meters. Was there a force? There is a force, but here's the thing. Within this question, the only place that I'm actually doing work is when I go up these stairs. So if I have a bag of groceries, what forces are acting on that bag of groceries? Okay. And so you're right. There's a force. In which direction is that force happening on that bag? It's on the sides, but what direction? Like, yes, I'm holding onto it, or my arms are underneath it, or whatever, or I'm holding onto the handles. Is the force that direction up, down, left, or right? It's going to be up. Because if I release my hands on that bag of groceries, what happens? It's going to go down. Why does it go down? Because of gravity. In Physics 11, we do a lot of these types of work. We do these diagrams. And often the question is, well, what forces are acting on this thing? And I tell them, your first answer is always gravity, because we're always dealing with gravity. So we're going to have gravity coming down, and so the force that I'm applying to that bag of groceries is up so that it doesn't fall down. So this is my force that I'm putting into this. What direction am I traveling? I'm traveling this way. And so what's the relationship between these two arrows? Why do we draw a square box there? What angle does that represent? And what angle is that? A right angle, 90 degrees. Okay. Does that make sense? Okay. So when I'm going up the stairs, what's my direction? How is my direction changing? Going up. So here is direction of 1 meter going up. Here's a direction of 5 meters, but the direction is horizontal. Here the direction is 3 meters, but the direction is horizontal. It's only in this section here that the force is going up and that the direction is going up. So technically that means this is the only place that I'm actually doing work on that bag of groceries when I'm raising it up. Does that make some sense? So my work here is going to be force. It would help if I actually did things correctly. So work is going to be force times distance, but we say that the force and the distance have to be along the same axis, along the same direction. So that's why this one's a little bit tricky here. So my force now is going to be 100 newtons, and times 1 meter, so that's equal to 100 Newton meters, or 100 joules, equivalent units for work. All right, 3 in the deep end. Let's go back and do a simpler one. Lots. Lots. Am I applying a force? Yes, I am applying a force. If we wanted to see that I was applying force, I could blow up like a balloon, and then if I push against the balloon, you see the balloon smushing out. So I'm not trying to trick you and say, oh, no. It's like, you make it look like you're leaning against the wall, but you're not really. No, I'm actually leaning against the wall. So I'm applying the force. I like doing the work. Why not? It's the long. So what's the distance that it's traveled? 0. there is no distance, there is no work. Okay? It's kind of subtle things that come out of this, but all right. So we're pushing a box, pushing that box with 15 newtons, and we're pushing it 3 meters. We want to know how much work have we done. Here's my box. Work is equal to force times distance. Is the force and the distance traveling along the same direction? The force is horizontal, the motion, the direction is horizontal. So work is going to be equal to our 15 newtons times our 3 meters. And so what we've done is 45 newton meters of work. So we're going to take a 7 kilogram box, we're going to raise it 2 meters. You want to know how much work has been done. All right. This 2 meters, what does that represent? Lifting up. So that's our distance. It's 2 meters. Here we have 7 kilograms. What is 7 kilograms? It's not how much it weighs. It's not. Is kilograms a unit of force? Isn't there mass? Does that make sense? So, does gravity act on that mass? Yes. Would I have to apply a force to lift it up? Yes. And the force that I would have to apply to lift it up, well, that would be about the same as the force of gravity that's pulling it down. Does that make sense? So, I know the distance, I just don't know the force yet. How do I calculate the force? Sorry? How do we calculate the force of gravity? We multiply our mass times the gravitational field strength. Does that make sense? All I'm doing in this case is just bringing, this is the first part we talked about, the force of gravity. And because we're working against gravity, we can still use that to calculate the force of gravity, or the force that we're putting into this. So we have to do this calculation before we can do that calculation. So we can take our 7 kilograms, what's G? 9.8. Why is it 9.8? Because we are on Earth, and that's the gravitational field strength. We're on Earth. So we can go 7 times our 9.8. That's equal to 68.6 newtons. .8 is pretty close to 10, so you can always check your answers. 10 times 7 is 70. That's pretty close to 7, so we've done it. Right. So now we can substitute this value into here. So our work will be equal to our 68.6 newtons times our 2 meters. And so our work would be 137 newton meters. Now, I'm writing joules underneath. I wouldn't expect you to do that. I'm just doing it to help reinforce the idea that newton meters and joules represent the same thing. We're good? Okay. So far, we've taken a look at the force of gravity in terms of our mass times the gravitational field strength. And we've taken a look at this concept of work being a force acting through a distance on an object, whether we're pushing it, whether we're lifting it up, and so on. We just have to make sure that the force and distance are actually going in the same direction, and then it will work for us. The next part is what we call the gravitational potential energy. And the symbol that we have for that is EP. Okay, so if I take 10 and lift it up, is there a force of gravity in 10? Yeah. Am I doing work on 10 by lifting it up? Are you afraid of 10? What do you do over there? 10 is over here. Are you afraid? No. If I was to hold this over top of your head, would you be afraid? Yes. Why would you be afraid? Why? If I dropped it, right? So, like, is this hurting you if I held this over top? Am I being hurt right now by this being over top of my head? No. If I dropped it, would I get hurt by this over top of my head? Yeah. I don't know. Maybe it would hurt. If I put this and rest it on my head, is that causing me damage? No. Actually, it's not great. But it's not causing me damage. So, if I was to drop this, what's it doing that it wasn't doing before? It's moving. If I drop it, it's moving. But if it's just sitting there, yeah, you need to do more force and stuff like that on it. Okay. The point is, all I've done is just changed its position. And I've applied a force through a distance to allow its position to change. Does that make sense? So let's take a look. There's 10. What I've done is raise Tammy, let's say 2 meters. What force would be acting on Tammy? So we're going to apply a force of gravity, or force of gravity is always acting on everything. Force of gravity is pulling Tammy down. If I'm raising Tammy up, am I applying a force to Tammy? In what direction? Upward. So there's my force. Is that in the direction of motion? So I'm taking Tammy from here to here. Is the force going in the direction that the object's moving? Yes. So how am I doing work? Yes, I'm doing work. So we know that work is equal to force times distance. Let's say Tammy is 5 kilograms. I need to calculate first the force of gravity. How do I calculate the force of gravity? mg. Newtons. Does that make sense? So now to calculate the work, I'm going to take my force and I'm going to multiply it by the distance. How much distance is there? 2 meters. Does that make sense? Have we done anything different that we haven't seen before? But we know that when Tammy's up there, I'm afraid, Hannah's afraid, you're afraid. We drop it. The reason why we're afraid is because we've given it the potential to cause pain, the potential to do hurt. Does that make sense? And what we've done is that we've raised what we call its potential energy. Does that make sense? So, what we did is that we did 2 equations here. We had the work, force times distance, then we did the force, and then we put that back into there. Okay? If we took our work, being force times distance, what we could do is that we could take this definition of how we calculated the force and put that in there for the F. Does that make sense? So I could say work is equal to, well, force was mass times g, and then multiply that by the distance. Are you good with that? When we talk about distances that are going up and down, what other word do we sometimes use for a distance vertically? If you saw a guy who thought was really tall, what question might you ask him? How tall are you, or what is your height? So we can talk about this as being height. And so if we change this to an h, we get this thing called mgh. This represents the work that's been done in order to change the position of that bowling ball from down here to up there. And when it is up there, it has potential. Sorry, I just got to respond. Actually teaching people. So we're going to define our gravitational potential energy. Everyone count. Phone time. As being simply mgh. Now, there were other, this is gravitational potential energy. There are other types of potential energy that we have. So if I have my Nerf gun here, I can pull this down like that. Right. Someone gets that? Excellent. So if I point this at you, Hannah, you're afraid. Why? How about if I pointed at you like that? Are you still afraid if I point like that? No. Why are you afraid if I point the gun at you? Yeah, I could pull the trigger because I pulled this down and I've given it. Okay, so now are you afraid? Why not? Yeah, this is no longer. So what we have in here is a spring. And so we can have spring potential energy. And so if I pull this down, I put energy into this, and there's the potential of this, it's going to come flying out. Does that make sense? So we can think of that like the springs or sort of like a bow and arrow type of thing. We can have potential energy when it comes to chemical energy. So like if I had a real gun that has a bullet in there, there's chemicals within the shell that can cause expanding gases to push the bullet out quickly, and that becomes not a good thing. So we're just talking about gravitational potential energy, but there's other types of potential energy as well. We don't do any calculations with those. It's just good to recognize that it's there. And so all we're doing is taking the mass, our gravitational field strength, and the height that we've moved things through, and we can ask different questions in terms of, well, how high is something if it has a certain amount of potential energy? Or if it is at a certain height and has a certain amount of potential energy, what's its mass? And so we can ask questions about EP. We can ask questions about mass. The algebra for that is we would have EP and G over G and H. We have to divide, these are all connected by multiplication, and so algebra tells us if it's connected by multiplication or division, we use multiplication or division, so we would divide these through on both sides. If we wanted to calculate the height, same thing, we're going to divide our EP by our mg and so on. And so because these have 4 characters within it, we cannot put it into a square or a triangle like we did with force and we can do with work and so on as well. We could actually calculate a gravitational field strength on an asteroid or something like that by taking a look at the potential energy, the mass, and the height. So when we've got a question with 4 letters in it, if we have a question with 3 letters in it, there's 3 types of questions we can ask, basically. If we have 4 letters, then there's like 4 types of questions we can ask. The mass, the height, the gravity, or the potential energy. Does that make sense? Okay. So a 3-kilogram ball is raised 1.5 meters. How much potential energy does it have? So we're going to go through other numbers. There we have 3 kilograms. What does that represent? That's the mass. Then we have this 1.5 meters. What does that represent? The height. Is there any other number in the question? No. What are we trying to find? EP. All right. So to calculate the EP, we look up on our sheet, we remember or whatever, use M, G, H. And then what we can do is we can substitute in our values. So EP, M, well, that's our 3 kilograms. G, that's our, G's not there. Did I forget something? Did they miss something in the question? What's G? You didn't say anything. Yeah, it's 9.8. It's our gravitational field strength. It's a constant. It stays the same on Earth. And then we have our H, which is 1.5. So the 3 times 9.8 times 1.5. So we have given that ball 44 joules of energy by raising it up. It has that much potential energy. That's also equal to the work that we would have had to do to raise it up at that point. Is this making a bit of sense, Riley? Sort of? Does it look so mysterious as it perhaps did before? Not quite the same. So, let's talk about kinetic energy. That's almost the last thing. Kinetic energy is what we call the energy of motion. So, Tammy is over there. Does Tammy have kinetic energy? Is Tammy moving? No. So if something's not moving, it has no kinetic energy. Does Tammy have potential energy? Yeah. If Tammy fell off of the filing cabinet and so on, there would be a big bang underneath. If there was like a carton of eggs underneath that, Tammy, as Tammy fell and hit the floor, would do work on those eggs and smash them. Does that make sense? Okay. But kinetic energy is the energy of motion, so if an object is not moving, there is no kinetic energy. The formula for this doesn't, like, the formula for potential energy came out of our work in gravity. This one doesn't come out of that the same way. This is just a straight formula where K is our kinetic energy, M is the mass in kilograms, V is the velocity. Sometimes we would use the word speed. Technically, they're different, but I don't care right now. And that's in meters per second. If you're in a car, how do we measure velocity or speed in a car? Kilometers per hour. Miles per hour in the States, in Canada, kilometers per hour. But the idea is that we have a distance divided by time when we're talking about speed or velocity. EK. K because it's kinetic energy, P when it was potential energy. Okay. So we can talk about a 3 kilogram ball moving at 4 meters per second. What is the kinetic energy? 3 kilograms, what does that represent? The mass. Then we have 4 meters per second. What is that number? The speed, the velocity. And for our EK. So we have EK is 1/2 our mv squared. 1/2 is just a number. Again, it's a constant, but whereas 9.8 is a constant because we're on Earth, this is a constant. There are reasons behind it being there. It's just a constant in essence that we have to put in there so the numbers come out right. It's not just willy-nilly. I made up a constant, the 1/2 is in there. No. So then we're going to go 3 kilograms, and then we've got our 4 squared. So 3 times 4 is 12 divided by 2, that's equal to 6. Very good. No. Need the unit. What would be the unit? It's energy. No, that's the symbol. The unit would be joules. Are we good now? No. What did I forget to do? No, the units are fine. The 6 is wrong. I went 3 times 4 divided by 2. 3 times 4 is 12, divided by 2 is 6. What's that? Square. So do I go 3 times 4, get 12, and then square 12? What's the order of operation? The brackets, there are brackets, but not brackets within the sense, exponents, and then division, multiplication, addition, subtraction. So what I have to do is I have to do this squaring here first. So what's 4 squared? 60. So now I can go 6, I can work back. It doesn't matter. Multiplication doesn't matter which way you do it. So in this case, I'm just going backwards. But like 4 times 3 is the same as 3 times 4. Division is not that way. What's 4 divided by 2? 2. What's 2 divided by 4? 1/2. Okay? So the order for this is important, but if you went 4 times 2, that's 8. 2 times 4, that's also equal to 8. So it doesn't, for multiplication, addition, it doesn't matter what order you do them in. For division and subtraction, it does matter. It's not a big thing. So I can go 16 times 3 times 1/2. 24 joules. That would be our kinetic energy. I'm making mistakes sometimes, like I did that on purpose, just to help you recognize, to help you see the importance of doing things in a particular order and not to forget that square. And that's an easy thing for students to do, for people to do. You just forget that it's there. You've got all the numbers, multiplication, bing, bang, bang. Okay. Should we do conservation of energy? It sounds scary. It's not bad. And that really finishes off what we're doing here. one way to talk about the conservation of energy is to say energy can't be created or destroyed, it just gets transformed. And so what we can do is we can take energy and we can change it into one form and then change it into another form. And the easiest way to recognize or to see that is in a pendulum. But when we talk about pendulums, let's just first review. EK stands for kinetic energy. What does an object have to have in order to have kinetic energy? Motion. So if there's no motion, then there is no kinetic energy. Does that make sense? And for something to have potential energy, there has to have been a change in height. What's a pendulum? We should start there. A shape. What do you mean by shape? Like a square, rectangle pendulum? I think you're thinking of parallelogram. Yeah. So I'm thinking, I've never heard that before. So a parallelogram is something like a box, but the sides aren't at 90 degrees, they're at different angles. So that would be a parallelogram, but that's not a pendulum. A pendulum, see that clock up there? See that, the leaf? Right now the clock's not working. It's not running. If we wanted it to run, what we have to do is we have to So, why do I have to pull these pendulums up? That's fine. I do not mind you saying I don't know. What do these... It's heavy. So these things have mass. Okay. Did I change the position of these? Did I make them higher or lower? Higher. So, in essence, what I have done is to give them potential energy. I have to raise them up. So I've given energy to these things right there. Now, watch what happens to this one here when I bring this down here. Good job. What happened up here? It made a noise. The cuckoo bird came out. Let's do that one more time. I like this. My grandfather, he liked clocks. All right, here we go. You just learned something and you're freaked out by it. Okay, so was there a change in potential energy here? Yes. Was there work that happened up here? Yeah, because there was motion and you could hear things moving and stuff like that around. So what we did was to take some potential energy and convert it into some kinetic energy up here. And the amount of energy that we used was based upon the change in height that's here. That makes sense. All right. For this to actually be running, that's what it's happening for. What is this called? And so in a clock like this, yes, that's called a metronome. And it's, in essence, it's working the same way. What we have is a thing going back and forth by changing where the weight. We have electronic ones, which are all different. slide it down. But why would you use that? When you are playing the piano, right? So it's helping you keep time. And because sometimes within music will slow down and then it'll speed up, but sometimes we want the music to be on beat and consistent. And that's what the metronome is doing. That's what a conductor is doing when he's waving his baton. He's saying how fast he wants the music to go. Slowly or fast. In a computer, one of the characteristics we talk about computers is the speed of the computer. We'll talk about, oh, it's like 2.4 gigahertz in speed. And what's the term comes inside the computer, you basically have like a metronome or a conductor who's controlling how fast calculations and things can happen in the computer. So if you can make him spin his baton faster, the computer's faster, gets more work done in a period of time. So there's a lot of places where these things come in. But here we have a pendulum, and the pendulum going back and forth, it always takes the same length of time to go from one side to the other. And so we use that for keeping track of time. Have you ever played like touch football and you can't get the quarterback until you've done something? Have you ever done this? Right. Because sometimes we talk about steamboats. You get 3 steamboats before you can, tag the. We would play football, right? And so you're not allowed to tackle the quarterback. You want to give them some time so everyone gets to play. If you've got a really good guy who's good at tackling, all he does, quarterback hits the ball and he's down on the ground. Quarterback hits the ball, he's down on the ground. It's not much fun. So you get 3 steamboats, and so the one team calls out 1 steamboat, 2 steamboat, 3 steamboats, and then they go after the quarterback. Or sometimes Mississippi, 1 Mississippi, 2 Mississippi, 3 Mississippi. And you're counting. Well, you can't. But why do we say like steamboats or Mississippi? That's fine. Sorry? Well, so it's about the length of time for a second. Because you said you have to count to 3. What to do? You're trying to keep to a consistent period of time. Learning something new about life. So that's really what's happening with the pendulum. As it's swinging back and forth, it sets out a certain length of time that was then converted into our minutes to keep track of time for us. Now, to adjust that, what's kind of cool is that this pendulum's always had a hemming part that moves up and down. And if I move this up, it goes faster. And if I move this down, here, it's slower. When I was growing up, we had a pendulum clock like this. And my dad was pretty particular. So over the course of many days, he would, there was a little screw at the bottom. He would adjust the pendulum weight up and down till it was as accurate as it could be. You never quite get it perfect because if it's moving really fast, that's counting too quickly, and it could be out, by several minutes in the course of a day. When you're getting close, it might be out by several minutes, but over the course of a week or a month. So, anyways, so a pendulum is an object that's moving back and forth. So, in a pendulum, the string is a fixed length, and so it's going to swing down and swing back up again. And you can think of you as being on a swing. There you go. And you're swinging back and forth. When are you highest on the swing? Yeah. So when you're at the furthest point up here, you're going to be the highest and staying back here. So strictly what how we recognize is that there is a height difference from when it's at the furthest reach and when it's right at the very bottom. Does that make sense? what sort of motion does it have at one of the extents? The highest point. How fast is it? So, when you're on a swing, do you ever go all the way around? No. You go out, and then come back, and go out, and come back. When you're at the farthest point out here, just before you start going back, how fast are you going? No, you're not. Sir, you're lying to us. Here, I have a very... I have a weight on a string. Okay? I can make it swing back and forth. When it gets to the furthest point out here, how fast is it going? Is it traveling any velocity? What's its motion like when it's out here? It comes out to one spot. So let's try this way. Here I have a ball, baseball. I'm going to take this baseball, I'm going to throw it up. Is it going to go through the ceiling and out into space? Probably not. It goes up, and then it comes back down again. So it goes all the way up. Does it stay there? Is it moving at that point? No, because it's going up, and it has to stop in order to start falling back down again. So, coming back to a pendulum, how fast is it going here? It's not. The velocity is 0. So when it's here or here, the velocity is equal to 0. So does it have kinetic energy? Not at that point. This is the key thing. At this highest point, when you're swinging out to here, when I take the ball and I throw it up into the air, when it's at its highest point, it's not moving up, it's not moving down, it's not moving. How long is it up there? Instantaneous, like almost immeasurable length of time. But it goes up and it stops and it comes back down again. Velocity is equal to 0. Kinetic energy is 1/2 mv squared. So if the v is equal to 0, what's 12,723 times 0, Hannah? 0. It's an easy question, because anything times 0 is equal to 0. So 0 here, the velocity is 0, the kinetic energy is 0. Has it gained height? Yeah. You know from swinging that, hey, you're highest up here. If you ever had a younger brother or sister that you're pushing on the swing, you're standing back here and get them really going fast and you're having to reach higher and higher in order to push them. And they're saying, higher, Daddy, higher. Higher, Hannah, higher. So they're gaining height. So they're gaining potential energy. And then they lose it as they come down. Does it have velocity here? Sorry? Yes or no? So when you're swinging back and forth, are you moving when you come through the center? That's your fastest spot. You come to a stop, and you swing back, go all the way through, come to a stop, swing back all the way through, come to a stop. So at this point, that's going to be our highest velocity. Yeah. What could you say about our height? Do we have height at that point? When it's at the lowest point. The height isn't changing. Like, so when you get onto a swing, the swing is hanging straight up and down, you get onto it, and that height never goes below that. When you start swinging, you go up, come through, and you go up. And so we can say that here, the height would be equal to 0. Do you have potential energy if the height's equal to 0? If that's equal to 0, what's 9.8 times 0? 0. So at this point here, where the height's equal to 0, our potential energy is equal to 0. Does that make sense? So what we can do, so we talked about the conservation of energy. Energy is not created or destroyed, only transformed. What we're doing here is we're transforming the energy back and forth between kinetic and potential energy. So when we swing up to its highest point, it stops. Kinetic energy is 0, but it has potential energy, and that's why it swings back down. When it's coming through the bottom, the height is equal to 0, it no longer has potential energy, but is it moving fast? Oh yeah, and so it has kinetic energy. And then it loses the kinetic energy to potential, and then it gains back, it keeps on going back and forth. And sometimes, I like slinkies for this. You ever taken a slinky and you make it go back and forth? So I think of this in terms of a slinky. My right hand, this is potential energy, and this is kinetic energy. The amount of slinky that I have here is set. So the slinky represents the amount of energy. But that energy is potential or kinetic, potential or kinetic, and it's always going back and forth as this is swinging through. Does that make some sense? So that's what we're talking about when we're talking about conservation of energy. Just type it. There we go. So we would say our kinetic energy at one point plus our potential energy at one point will equal our kinetic energy at another point plus our potential energy at another point. It's like a clown. So, our potential plus kinetic at this point equals our kinetic plus potential at this point equals our kinetic plus potential at this point equals our kinetic plus potential at that point or at that point or at that point. At any point, the amount of kinetic plus potential is going to equal the same value at any other point. The amount of slinky I had between my two hands was always one slinky's worth. Sometimes it was more in one hand, sometimes it was more in the other hand. Does that make sense? But what we do is that we take a look at the special cases. And the special cases are when it's at highest point, because then we say it's all potential energy, and it stops, so it has no kinetic energy. And so then we look at the bottom, and we say, hey, it no longer has potential energy, it's at its lowest point, so it has all kinetic energy. Does that make sense? Can you understand? Now, we sometimes throw into here something called heat. Sorry? I put this in brackets because we don't always consider it. If we set up a pendulum swinging back and forth, it will swing for quite a while, but eventually it gets less and less and less and will slow down. Why does it slow down? What's momentum? And I love it when students say that because I jump on them and beat them and say, don't use words that you're not quite sure of. So you're right. We have a casual way of using momentum, like we have a casual way of using weight and mass the same thing when they're different. Within physics, momentum has a very specific meaning. And that's where you take, and you're right, it does come into here, but we have never talked about momentum. Momentum is found by taking the mass of the object times its velocity. So it's sort of related to kinetic energy. It's part of that, but velocity is not squared, and there's no 1/2 term. So, as I said, be careful when you're using words unless you really understand, like in the science classroom with the science teacher, unless you really understand what that word means. But we have motion and we don't have motion, and we have this changing back and forth. And I forget the question I was talking about, but pendulum swinging back and forth. Eventually, it slows down, and yes, it ends up losing momentum. It ends up losing energy. But we said energy can't be created or destroyed. It's only being transformed. Why do you think a pendulum would slow down? Because it runs out of energy. But where's that energy going? We're losing energy. Stop to me. Okay. So if you're running around the track, what do you feel in your face? What? Oh, I thought you said weak. You feel weak. What? You feel the wind. You feel the wind going through, makes your hair blow behind you. Right? So when you have that pendulum movement, here on Earth, you have a pendulum going back and forth. It's always having to push through air. Now, air's not hard to go through. It's not like running through water. Sometimes people try to run through water as exercise. You're having to push a lot of water, and it's difficult. The pendulum in air is losing some energy to the air molecules as it bangs into them, and they take away some of the kinetic energy and so on. That's there. And so that's why things slow down, because we're losing energy. And so we would talk about that energy as going into heat. We'll do a question. One of the questions talked about a kid sliding down a slide. Have you ever gone to the top of the slide and just jumped off? No. What would happen? You would hurt yourself. And you would hurt yourself because you have potential energy at the top of the slide that's changed to kinetic energy at the bottom of the slide, and it's the kinetic energy hitting the ground that hurts you. When you go down a slide, it's the same change in potential energy. One of the things is you're going out sideways. Here's the thing. If you were to fall off a slide, the velocity that you're hitting the ground would be the same as the velocity that you'd be coming off the end of the slide if there wasn't a friction. And sometimes on slides you have friction. If it's been wet out, so on, it's really hard to go down the slide. It's not much fun. But if there's, other times it's dry and the slide right down, but there's still friction slowing you down. And that friction, like we talk about heat, you take your hands and rub them together. How do your hands feel? Warm. And that's the heat that comes from the friction. So when you have friction and things moving through air is friction, that's actually heat energy being removed from the system. Does that make sense? So here we have a question. We have 0.5 kilogram pendulum is 0.25 meters high. What is the maximum velocity? When does it have its maximum velocity? 1, 2, or 3? 0 velocity at 1 and 3. So 2. Because here it stopped, because it's changing direction and going back. Stopped, and changing direction and going back. At what point, 1, 2, or 3, does it have its maximum potential energy? 4 or 1, because they represent the same height. So we can say for our conservation of energy that our EP1 plus our EK1 is equal to our EP2 plus our EK2. How do we calculate potential energy? Equal to mgh. Call that height 1. How do we calculate our kinetic energy? We'll call that velocity one. So our potential energy plus our kinetic energy is equal to our mgh2 plus our 1/2 m v2 squared. So at point 1, does it have height? Yeah. 0.25. Does it have mass? It's a pendulum. We're not losing mass anywhere. The mass is there. So we could take our mass, 0.5, g is 9.8, and our height is 0.25. Okay? Mass, still 0.5. What's its velocity at point 1? Like, how fast is it going? What's the speed? Nope. Because when it's at its highest point, how fast is it moving? 0. For it to come out, like, how fast is the ball traveling at the highest point? It goes up, and it has to stop, and then it comes back down again. So the velocity is 0. For a pendulum, it swings out, stops, and then swings back and stops, and then swings back and stops. And it's always stopping, briefest of moments, an instantaneous amount of time, but it has to come to a stop because it's changing its direction going back the other way. So what's the velocity value for 0 for stop? So at its highest point, it stops. The kinetic energy is going to be equal to 0. All right, so at point 2, we have mass, 0.5, 9.8. What's the height at 2? Nope. That was the height at its highest point here. Is it higher or lower at this point? It's lower. So the height is going to be 0. What's anything times 0? 0. And then, does it have velocity at this point here? Does it have velocity out here? Speed. Is it moving at this point here? Is it moving at this point here? Yeah, because it's swinging through. And that's where its maximum velocity is going to be. So that's what we're going to try and find. Is this making a little bit of sense? So this part goes to 0. This part goes to 0. So I'm going to rewrite this question, but I'm just going to get rid of those because they're 0. So we have 0.5 times 9.8 times 0.25. That's going to equal 1/2 times 0.5 times our v squared. How many things do we not know? Just the velocity. So this is how we can calculate and work out what the velocity is. And it's because we have this transfer of energy from potential to kinetic to potential, back to kinetic to potential, and so on. We're shifting the slinky from one hand to the other. All right, so let's just do our numbers and we can see how we work this out. We have 0.5 times 9.8 times 2.25. So 1/2 times 5. So we're going to have to divide both sides by 0.25. Have you done this in math? Like, so if I got to here, you'd be able to solve the rest of that? Okay. I just wanting to check. So not wanting to do more math than you're comfortable with, really. Yes, I am. All right, 1.225. Sorry? No. That's the velocity squared. So how do we find the velocity? This is velocity squared. What's the opposite of squaring something? You have to square root it. So there's our velocity, 2.2 meters per second. It's a nice smile, Riley. There are a lot of numbers. There are a lot of numbers, and there can be. But it's just multiplication, division, addition, and subtraction. And that's all we've done. That's all of the physics part. Yeah, yes I can. Okay. So you have some worksheets, there's some things to go through, and I would recommend you go through those. And as questions come up, ask. Does that make more sense for you? Okay.